Okay, so let's first, do the basics. So this is a dynamic programming algorithm for solving the longest common subsequence problem. And in this problem, we're looking for the longest common subsequence between two strings. And like I said last time, in every dynamic programming algorithm, the key idea is to look. Well, first you solve some base cases that are easy or usually trivial to solve. So you solve the trivial base cases, and then you start, and based on the solutions to smaller subproblems, you construct solutions to bigger subproblems. And in this case, the bigger subproblem is the optimal solution at row I and column J. This is row I and column J. And what are the subproblems that we look at in order to figure out the optimal solution for at I and J? In fact, in this case, we look at how many subproblems in order to determine the optimal solution at I and J. Yeah. Okay, so AI, this, I minus 1, well, this is J minus 1, and this is I minus 1. So yes, so I minus 1 and J minus 1. Is this the only one that we look at? No, we also look at I minus 1 and J and I and J minus 1. We look at all three here. So if A of I and J, if S of I equals T of J, what do we do? If we have a match between the two strings at I and J, what do we do here? Yeah, exactly. The diagonal, which is I minus 1, J minus 1, plus 1. Now, if they don't match, then our best solution, so if we don't have a match here, then our best solution is the better of this and this. So we look at this, and we take the better solution. Of course, if they are the same, we take either one, but the structure of the code will determine which one will get taken if there is a tie. Because if there is a tie, if this and this have the same value, it will be correct to take either one. Which one will get taken? That depends on how you write the code. Okay, so I will ask this question after we write the code. So if this one is better, well, if this one is, what does it say, greater than or equal here? Yeah, greater than or equal. Of course, we can get rid of the equality. So if this is greater than or equal to A of I and J minus 1, then the solution is what? A of I minus 1 and J. Else, the solution is A of I and J equals I and J minus 1. Okay, so now if there is a tie, what do we take? Not usually. No, there is a definite answer depending on the code. What does this code take? Yeah, because this code with the equality, we take I minus 1J. And I minus 1J means previous row, same column. So it's this. I minus 1J is this. Previous row, same column. So we go up up instead of left. So you either take from the upper cell or from your left neighbor. In this code, you take from the upper cell. Now, if you remove this equality, if you make it greater than, you will be taking the left neighbor in case of a tie or equality. Okay? All right. So I think, does anyone need more time to do the tracing? So let's do the tracing because it's straightforward, or applying the algorithm to an instance. So in this case, null mean nothing with nothing. So it's going to be 0, 0, 0, 0, 0, 0. These are filled here. So when there is no string, the length is when one of the strings is null, then there is no common subsequence. The length of the longest common subsequence is 0. So these are the zeros that we set here. Now we start from I equals 1. This is I equals 1. Now we look at the diagonal. It's 0. Do we have a match? No. So it's a 0. So do we take from, and what do we take from? Up. And here, is there a match? Yes, there is a match. So it's a 1, and we are taking, well, let me do that in blue, I think. It will be less messy to draw this in blue. Okay. Okay, this is diagonal and this is this. Okay. Now, next, match. Is there a match? No match, but left is greater, so we take the left. So this is the left. Here, match. No match, so we take the left because the left is greater. Here, match, so it's diagonal, and it's a 1. Here, no match, and we look at the one above it and the one to the left. They are both the same, so we take from the top. No match, we take either one, so the algorithm will take the upper one. Here, there is no match also, so we continue to take from the upper cell. No match. Here we have no match, but we have no choice but to take from the upper cell. No match and a tie, so we take from the upper cell. Match, so we take diagonal. 1 plus 1 is 2. No match, but left is greater, so we take from left. And no match. No match, we take from upper. No match, so we take the 2 because it's greater. And finally, there is a match, so it's diagonal, and we take a 3. So what's our longest common subsequence in this case? We trace it backwards. We start from the last cell. So this means that there is a match on A. So A is taken. Then we go back to this here. Do we have a match? Yes, we have a match. So the B is taken. Then we go diagonal. There is no match, so nothing is taken here. We trace it up. Here is a match, so we take the C. So CBA is the longest common subsequence that we take in this case. Yeah. Is it the only, is the optimal solution here unique? No. There is another optimal solution, which is, DBA. But each, depending on how you write the code, then you will find only this code finds only one optimal solution. So in fact, if I change this greater than or equal to greater than, I will discover the other solution, the other optimal solution. And always keep in mind that in general, an optimization problem may have multiple solutions. Questions? All right, work on the next question, please. All right, so now part C. The question is, we would like to change the base case from size 0 to size 1. So we would like to eliminate these, the first row and the first column and limit ourselves to this. So now, what does the base case mean? Who can define a base? What's a base case? How would you define it? What do we mean by a base case? So there is a base case and there is a recursive case. So the base case is the case that's solved directly. It's not solved based on previous solutions. So now we would like to write a formula for filling in these ones directly without referring to a previous case. So how do we do that? If what they are, when you say they, what do you mean? Okay. Okay. So let's first focus on the first row. How did you find the solution for the first row? What do you mean it's equal? This is not precise. What is equal to what? Yeah. The characters S of I is equal to T of J. If S of I is equal to T of J, then the answer is 1. Else it's 0. Exactly. That's the point. So it's not just, we look at the first row and we compare S of 1. So in fact, we can write the code. If S of 1, of course, we go from for J equals 1 to N. So this is J goes to N all the way to N. And this is I that goes to M. So for J goes 1 to N, if S of 1 equals T of J, then A of 1 and J equals 1. Okay. Now, do we just say else it's 0? If we say else it's 0, then what will we get? Then this would be 0 and this would be 0. So we can't just say else it's 0. We fill in, once we find a 1, in fact, once it's a 1, all the rest are going to be 1s. That's the point. Once we get a match, then the rest of the cells in that row will be 1s. Okay, so then once we get a 1, we go from K, for K equals what? for k equals j plus 1 to n, we set a of 1 and k to 1. And then, in fact, we break. We break at this level. There is no need to continue. Now, else, what a of, what should I put here? Else, if it's not a of 1 and, no, this has nothing to do with k now. K is for filling the rest, j. A of 1 and j equals 0. So this is the point here. The point is, once you find a 1, you fill the rest with 1s. Okay, questions? Okay, so in fact, I'm not going to do the column. It's just the dual of that. So the longest common substring, which was explained in the recorded lecture, the idea is to check if there is a match with the longest common substring. If there is a match, yeah, we continue and we go diagonal like this. So, well, here 0 0 0 0 0 0 0 0 0 0 0. So if there is no match, we don't have anything. No match, nothing. No match. Here we have a match and it's a 1. So our longest common substring so far is A. Okay. Now, no match, A and E. Now, what do we put here? Is it 1? Yeah, it's 0 because it's a string. The string has to be contiguous. So in fact, when we get a mismatch, we start over. We start searching for a different string. So it's a 0. And here, match, then it's a 1. Mismatch, it's 0, 0, 0. That's easy. So it looks like there will be lots of zeros. But how will we find the longest common substring? We'll see. Now, this is 0. Mismatch, 0. Match, what? Diagonal. So this is a 2. Now we found a substring. You know, this with this 2, this means that we have detected this substring, BC. Okay. Now, mismatch, we just put a 0. Mismatch, 0, mismatch, 0. Now, how will we keep this 2? How will this algorithm keep the 2? What's the main difference between this algorithm and the longest common subsequence algorithm? We create. So the difference in behavior, where is the optimal solution? How do we find the optimal solution in this algorithm? Exactly. The optimal solution is just the largest number in the table. It's not necessarily in the last cell. And this is a good example because it shows you that in dynamic programming, the optimal solution is not always going to be the last solution that you compute. Sometimes it's somewhere in the middle. So here, 0, 0. Now I have a match. So I go diagonal, and that's a 3. Okay? So now my longest common substring got extended to this. This is my longest common substring. And then 0, 0. And here, the E is going to be 0, 0, 0, 0. But the E matches with the E. but the diagonal here gives me only a 1. So the point is that my optimal solution is not necessarily in the last cell. Here is the biggest number in my table, and this is my optimal solution. So in terms of the code, what we have been doing clearly is if there is a match, we go diagonal, else we just set it to 0. That's the algorithm. It's a simpler algorithm. But now I want you to think about writing the code that will print the string, the actual string. A of I and j equals, let's, okay, I'm going to do this. Else why did I leave space here? Because we need to do something to keep the optimal solution. Let's see how much time we have. Okay, I can give you 2 minutes to work on this, and then I will answer it in 2 minutes. Okay, so what do I need to do here in order to get this 3? Well, I need to store the value of the maximum as well. So I need to store maximum, well, let me do it in blue. Maximum length equals 0, and maximum, do I need I and j or only I? I think you can do it with only I. I don't think you need j. Why? Because once you determine that your I, the I at which you found this, you can just go back in that string because it's contiguous, right? So you no longer have arrows that you need to trace. So it's just you go back in that string. So if you tell me what's I in this case, what's the maximum I? So this is 1, 2, 3, 4. So all what I need to know is that I, maximum I, or the I at which I had the maximum, is equal to 4. And then I know the length, and maximum length equals 3 in this case. So I need to print S of, well, this is I equals 4, so S of 4, S of 3, S of 2. So I need to print S of 2, S of 3, and S of 4. That's what I need. This is the longest common substring. Okay, so in the code here, if A of I and j is greater than maximum length, then maximum, well, let's put it here. Then maximum length equals A of I and j. And maximum I equals I. And then to print the string, just for, well, let's do k. Or in fact, I can reuse I because I'm outside the loop. So I'm going to do this outside the loop. For I equals max I minus max length plus 1 to max I. So max I, just print S of I. S of I. So I go from max I minus max length plus 1. So in this case, max I is 4 minus max length is 3. So that puts me at 1 plus 1. That puts me at 2. So I go back and then I print backwards. I print the smaller index first. Okay? Questions?